So you see this, right? It might look like just a bunch of tangled, complicated logic. But what if I told you there's a powerful toolkit that can transform all of this chaos into something incredibly simple and elegant? Well, that's the magic of Boolean algebra. It's a set of rules for turning complicated logic into pure efficiency. Let's dive in and see how it works.
All right, check these two expressions out. The one on the left, wow, it's a tangled mess of parentheses and negations, a real mouthful. But the one on the right, it's just X or Y. The difference is night and day, isn't it? One looks like a total headache to figure out, while the other is just beautifully simple.
So that brings us to this central puzzle here. How in the world can these two things be logically identical? It seems impossible, I know, but I promise, by the end of this, you'll see exactly how it's done and you'll get the elegant rules that make this amazing transformation possible. To solve our puzzle, we need to open up our toolkit. Now, these laws aren't just some abstract math you have to memorize. Think of them as practical, powerful tools we're going to use to methodically chisel away at complexity until only the simple truth is left. First up, we've got two laws that should feel pretty familiar from basic math. The commutative law just says that order doesn't matter. X and Y is the exact same as Y and X. And the associative law? That just means grouping doesn't matter, so you can move the parentheses around however you want. Simple, right? These are our basic rules for just rearranging the pieces on the board. Next up is the distributive law. Now, this one is a key tool for reorganizing our expressions. It shows us how we can take an operator that's outside of parentheses and distribute it to the terms inside. This lets us break things apart and then reassemble them in new and often much simpler ways. Okay, now for De Morgan's laws. These might seem a little less intuitive at first glance, but man, are they powerful. They give us a very precise recipe for what to do with the not that's hanging over a whole group of things. The trick is, it flips the operator inside. An or becomes an and becomes an or. This is an absolutely critical move in our simplification game. And finally, we have our cleanup crew. Idempotence is just a fancy word for a super simple idea. X and X is, well, just X. It gets rid of repetition. And double negation is even easier. Two nots literally cancel each other out. These are the tools we'll use to polish everything up at the very end. All right, we've got our tools. Now it's time to get our hands dirty and tackle that puzzle from the beginning. Let's see if we can transform that complex beast into its simple counterpart, one logical step at a time. Here it is again, in all its tangled glory. Our mission, should we choose to accept it, is to apply our new rules, one by one, very carefully, to whittle this thing down to its absolute core. Okay, first step, we need to find a pattern that matches one of our rules. See that not X or Y tucked away in there? That is a perfect candidate for De Morgan's law. So let's apply it. Now, wait a second. The expression actually got longer. That feels totally wrong, doesn't it? But you've got to trust the process. Sometimes you have to make things just a little bit more complex before you can make them simple. And see? That little detour pays off immediately. Because we now have a string of ands, the associative law lets us regroup. We can just slide those parentheses over to group the two not X terms together, which sets us up perfectly for a major simplification. This is where our cleanup tools come into play. We've got not X and not X. Thanks to idempotence, that whole thing just collapses into a single not X. And just like that, poof, we've eliminated the redundancy and the expression is already a whole lot shorter. So let's look at our new, cleaner expression, not X and not Y. Hey, does that look familiar? It should. It's the other side of De Morgan's law. So now we can use the rule in reverse to consolidate those terms back inside a single not operation, giving us not X or Y. And here we are, the final step. We're left with not of X or Y. A not of a not. This is a textbook case for double negation. The two nots simply cancel each other out. And what are we left with? X or Y. There it is. We did it. We've proven they are exactly logically the same. Now, this might seem like just a neat mathematical party trick, but it has massive, and I mean massive, real-world consequences. This exact process of simplification is fundamental to how we build every single piece of technology around us. You see, if we wanted to build a physical circuit to compute our original messy function, we'd need 5 separate components, or what we call logic gates. We'd need 3 for the not operations, 1 for and 1 for or. That's 5 little pieces of silicone. But after our simplification, we proved that the logic is identical to just X or Y. And to build that, we only need one single component, an OR gate. We get the exact same result with just one piece of hardware instead of 5. And this, right here, is why it all matters so much. By simplifying the logic on paper first, we get an 80% reduction in physical components. That means our circuits become dramatically cheaper, smaller, faster, and way more power efficient. This isn't just theory, it's the foundation of all modern engineering, and it happens billions of times inside every single device you own. So that whole process seemed pretty straightforward, right? You just apply a few rules and you're done. But here's the twist. What we just did, finding the absolute simplest form, is actually far from simple. You know, our example was pretty manageable. But for a really, really complex function, the task of finding its absolute simplest form is considered one of the hardest, most famous unsolved problems in all of computer science. The process really relies heavily on intuition, experience, and sometimes even just a little bit of luck. This problem belongs to a special class of problems called NP-hard. To put it simply, that means there's no known algorithm, no magic shortcut that can take any complex logical expression and guarantee you'll get the absolute simplest answer in a reasonable amount of time. It remains a true intellectual puzzle for both humans and computers. And that leads us to one final, kind of mind-bending question. We've been working with 3 main operators this whole time, and, or, and not. But are all of them truly necessary? Do we actually need all the tools in our toolkit? Let's just try a little thought experiment here. We can actually prove one of our core operators isn't really fundamental at all. Let's start with one of De Morgan's laws. Now, what happens if we apply a not to both sides of the equation? Well, on the left side, we get a not of a not, which is a double negation, and that just cancels itself out. And look at what we're left with. This beautiful little equation proves that the entire OR function can be built perfectly using only and not. OR is fundamentally redundant. Yeah, it's a useful shorthand, but it isn't essential. And what that means is, at the very deepest level, the entire vast complexity of modern computing is actually built on an even simpler set of tools than we ever imagined.